All right. Sorry about that. So on Monday's class, we were talking about qualitative data mostly, and we were looking at frequency tables, and we looked at some bar charts and some pie graphs for those. From this point forward, we might look at some qualitative data, but the vast majority of the stuff we're going to be looking at is quantitative data, because obviously we can't do calculations with the qualitative data. So, and the class would be kind of boring if we had no math involved in a math class. So we're going to start looking at quantitative data. The first thing we did with qualitative data was we started making frequency distribution. So we tried to organize that into some kind of table that we can turn into graphs. The difference when we look at quantitative data is we have to somehow group it before we can put it into those tables. So look at this. So let's look at, we have 50 heart rates of our students, and we've got this table of 50 values. If I was just to ask you what patterns do you see in that table, it would be very difficult for you to decide anything. So we want to organize it. So over here we have our frequency distribution. And you'll notice that they seem to organize it. They started out at 57, went to 66. So they did, so how many is in each group? How many different numbers did they look at in each group? 9 or 10? Okay, so one of the things that we're going to look at, and we're going to do this a bunch, is when you're looking at your numbers, if you subtract them, you're going to get 9. If you count them, you're going to get 10. So we want to go with the counting because we actually include the endpoints. And that's where when you subtract it, you lose one of the endpoints. So they just chose groups of 10 and put them together. And they started at 57. What's the smallest value in those heart rates?
97.
Oh, no. Oh, sorry. In the table. In the actual, like, the list of all the values. What's the lowest heart rate? Is there a 57?
62.
62 is the lowest. And what's the highest? 98 is the highest. So as you can see, their table looks at values that aren't even in our list. Okay. And that's because of how they actually created that frequency distribution. So let's start looking at how we actually do that. So the first thing we want to do when we're trying to create a table of values or a frequency distribution for a list of them is we want to decide how many classes we want to look at. So if we look at this table, the classes are how many rows we have. So how many classes did they pick? So they had 1, 2, 3, 4. They have 5 classes. Each row is a class. Okay. So they chose 5 classes for this frequency distribution. That's completely arbitrary. You could have chose 6. You could have chose 10. You could have chose 4. It doesn't matter how many classes you choose. The goal is to choose enough classes to be able to figure out what's going on in the information, and not so many like that pie chart we looked at on Monday that had like 40 values all over the place. You don't want to pick too much because that spreads out the data too much, and you're not going to be able to see what's going on. The same thing with too little. So typically you want more than 4 because 2 or 3 really doesn't give you much information. 5, 6, 7, sometimes up to 10 classes is enough typically. It also depends on how much data you have. If you have thousands and thousands of data points, using more classes would be fine because you have enough data to spread it out. So in this case, we only had 50, so 5 kind of makes sense and works. Okay. So this case, purely arbitrary, you just picked a number. I'm going to go out on a limb and go, most of the questions on Hawks will probably tell you how many classes you can choose, are going to choose, because otherwise they're not going to be able to tell you if the answer is right or not. The next thing we want to look at is we need to determine the class width. So once you've decided how many classes you're going to have, Now we can start doing some calculations to determine how we're going to set up our table. So to do this, we need 3 pieces of information. We need our maximum value, which, if I remember right, you said was 98. And we need our minimum value, which was 62. And you're dividing by how many classes you chose, which in this case, they chose 5. So take out your calculators and come up with the answer. And nobody shout out the answer, because I want to make sure you can use your calculator correctly. All right, everybody got an answer? Did anybody get something other than 7? What'd you get? 7.2. Okay, 7.2. All right. Hold on. Let me actually do it the other way just to find out what that actually answer would have been. Did anybody get 85.6? Good. And y'all can use your calculator correctly. It's actually, as crazy as it sounds, really important. Because when you're starting to do these calculations, if you don't know how to actually get the right answer on your calculator, and you really don't know what the answer should be, you're going to get an answer that might not make sense and you won't know. So you should have gotten an answer. I think this one comes out to be exactly 7.2. Okay, so my class width is 7.2. So why'd they choose 10? So you can use pretty much any number you want, as long as it's bigger than that number. Okay, so if we looked at this and we said, okay, let's do 6. Actually, we'll do the right one first. I'm going to do a class width of 8. Okay. So if you notice when they did it, they did 10 and they started at 57. Do we have to start at 57? No. What's the lowest number that we have to have in our table? 62. So we have to start at least 62. I'm going to start at 60 just because I want to start an even number. So again, it doesn't make much difference where you start. So I'm going to go 60. I want a class width of 8. So this right here is known as my lower limit of my class. So what number is it going to? 68 or 67? It's going to go to 67. You might want to just go, oh, I'm going to add 8. Remember that whole concept of subtracting? You get 1 extra, you lose 1. The thing happens if you added it, you're going to actually add an extra number. So if you're going to do that and just add a number, always subtract 1 to add the number. So if we're looking at a class width of 8, we would add 7. Okay, because plus the number you're originally starting with gives you your 8 values. Okay, does that make sense? Very important. Biggest mistake people make when they do this. So the 67 is known as my upper limit. So your lower limit is 60 and my upper limit is 67. That's class 1. How many classes did I want? I wanted 5. So my next class is going to start at 67. Or sorry, not 67, 68. It's going to start at 68. It's 1 number higher. And it's going to go to what? 75. It's my next class going to start at 76 and go to. And then 84 and go to. And then 92 and go to 99. So I have 1, 2, 3, 4, 5 classes, correct? Do I have enough basically buckets or classes to put all the numbers into? Yeah, because my smallest one was 62, my largest one was 98, right? So I'm good. I could do this with a class with an 8, no problem. Okay, and with a little extra wiggle room on either side. What happens if we did a class with a 6? Let's start exactly at 62. Because that's the lowest I can start with. Or the highest I could, that's the highest, yeah. So 62 is going to go to what? 67. 68 is going to go to 70. Yeah, 70 into 73. Yeah. 74 is going to go to 80 is going to go to 86 is going to go to. I have 95 classes. I'm sorry, 95 classes. I have 5 classes now. Do I have enough places to put all my numbers? No. I would need a 6th class. I would need to go 92 to 98. So you don't want to go lower than that number. Even if I did 7, I would have been off by a little bit at the end. They're asking about everything. So when you're looking at this type of problem, they're typically going to give you a table, and you're going to have to create the table, the frequency distribution for it, which they'll most likely tell you the number of classes, because again, they want you to very specifically do it. And then from there, you're going to come up with your class width, and then your count, the actual values in each of those spots. Okay. So it's one of those things, like I said, like you can sit there, they did 10 for their class width. We did 8 over here and still would have been fine. Even if we did this and made the table, the numbers in that table here would not have been exactly the same. Okay, it wouldn't have been 2, 10, 32, 5, and 1, because our range was different. Our upper and lower limits were different. But we still would have had a place to put all the numbers. Does that make sense? Or no? Okay. So we found our class width. We found our class width we did 8. We made our 5 classes, and we have our lower limit and our upper limits for it. So that's the third thing you want to do after you find your class width, is to find the class limits, the upper limit, lower limit, which we did. The next thing you want to do is determine the frequency for each class. So in this situation, what we would do, don't try to write all that down, is we would go back to our table, and we would basically use tally marks. Don't sit there and go, okay, 77, or let me say, I need 57 to 66, and try to sit there and count through them all. Okay, I got 1, because odds are you're going to miss something doing that. It's way easier to just take this and go, okay, 77, I got 1 there. 84, I got another one there, and just do tally marks in it to count the number of values in there, and then turn that into an actual number. Okay. So in this case, I'd have 2 tally marks here. I'd have 10 here. I'd have 32 here, and so on and so forth if I went through and counted them all. Now you can see why, if I did that here, if I did the class width of 8, like I did here, then those tally marks would be in different boxes. Okay. Because this one went to 66, and this one going to 67. So the 67s would be in this box instead of the second box. Okay. But both of those would be correct. It's not that doesn't make a change in the actual data. And it would still give you a nice curved data that you'd be looking at. Okay. Does that make sense? Okay, so here's what we're going to do. You're not going to do the tally marks because I'm not making you do 100 of them. That'd be insane. What I want you to do, though, is I want you to figure out the class widths and the upper and lower limits for all those class widths. I want you to do, for this one, 6 classes. Okay, so you're going to have 6. So you're going to have 6 classes for this one. Let me get out of the way. So what pieces of information do you need?
And maximum.
Minimum, maximum, and then I gave you the classes. Huh? Oh. All right, what's the minimum one? Minimum is 55.2. Actually, I think, hold on, was it? Yes, it was 55.2. And what's the max? Okay. Now everybody should be able to do it even if you didn't find those numbers. So we're going to do 71.6 minus the 55.2 and divide by 6. And what do we get? Okay. These numbers actually have decimals in them. We could technically do 2.8. We're not going to. Which class width do you want to use? Yeah, I'd probably use 3 for this one. I think 5 would be a little too much. So yeah, I'd probably do 3 for this one. All right, so you've got 3. Make them my classes. I want 6 classes with a class width of 3. What do you mean?
If I choose 71, if I choose 55.
Yeah. You go to 57. 58 would be 55, 56, 57, 58. That'd be class with a 4. Did anybody start at something other than 55? Oh, you started exactly 55.2? I wouldn't have started 55.2. The whole numbers just make your life easier. You don't have to. The other thing is you don't really always want to start at the exact number. So like even if at like the last one it was 62, I probably wouldn't have started at 62. I probably would have started at 61. Just to get a little bit of wiggle room there. But yeah, you can use decimals. It just makes life easier if you don't. It's like these had them in there, so you can use that extra flexibility. So I'm going to start at 55. So 55 to what? 57. And then 58. And then 61. 64. And then 67. 69. And then 70 to 72. Can I get all the values in there? What about 60.4? Where's that going? These technically are to 0.9. Because I have one decimal point, I have to have that piece in there. So I would look at those to 0.9 and plug them into those values there. Huh? Yeah. So 60.4 would go into this one. 60.4 would be in that one. You do have to make sure your numbers work for the data you have. So that is one consideration to keep in mind. All right. Class width? Class width in this case is 3. Oh, your lower limit, the first one's 55, then 57.9, 58, and then 60.9. Yes, but we're not using, we're not doing the decimal piece, so that's fine. Yeah. Yes, technically you are correct. It'd be 3.9. You're going to have whole number ones on the homework and the test and stuff, though. And there's another way to do these when you have a lot of these decimals and stuff.
When they if you're asked to do this on a quiz, would you want to include 0.9?
If you're going to do this on a quiz, you're going to have whole numbers, so you won't have to worry about it.
Okay.
And I don't believe Hawks uses anything but whole numbers on theirs either. So once we get past the frequency tables, you're going to be looking at doing it in histograms and stuff like that, and we take care of that problem another way in the histograms. So we'll see that in a minute or a few minutes. All right. After we make the frequency table, we have a couple other calculations and things that we can actually do with it. The next the next frequency distribution you can have is a relative frequency distribution. Just like we did with the qualitative data, made them into percents, that we could use that to make a pie chart. You can do the same thing with these. So a relative frequency distribution would be just the number divided by the total amount. So in this case, 2 divided by 50, 10 divided by 50, and so on. And you get them as decimals or percents. So remember, decimals, a percent is just moving it 2 places. So 0.64 is the same as 64%. Being able to go back and forth between those two is very helpful, and you're going to be seeing those a lot. So just remember, move 2 decimals, you get your percent. So that's a relative frequency distribution. Nothing crazy about it, just divided them to figure that part out. We also have 2 what are known as cumulative frequency tables. We have a cumulative frequency distribution where cumulative frequency is literally just adding up as you go. So my first class, I have a cumulative frequency of 2. My second class would be 12 because it's 2 plus 10. Third class would be 44 because it's 2 plus 10 plus 32. So you're just adding as you're going. So it's a running total, basically. And the last one is a relative cumulative frequency, where you're doing your running total of your relative frequencies. What does every relative frequency table have to end up with? Huh? What's the last one always have to be? 1 or 100%. Okay? Your relative frequency table always has to add to 1 or 100%. It can be slightly off depending on how you're rounding. If you have to round for certain ones, there is a possibility when you're sitting there rounding, you add them up and you get like 99.9 or 0.999 or 1.001. Like those, it could be off by a little bit when you're rounding. That's okay. It's not the end of the world. It's not a mistake you made. It's a rounding error. So normally they take care of themselves, but not always. All right. So after we made our table on Monday, we then did what with it? After we did tables in class on Monday, so I talked about the frequency tables. What did we then do with those tables? We made it into a chart, made a graph, right? Because pictures are worth 1,000 words. We wanted to make graphs. And we're going to do the same thing here. So this, what does this graph look like? It's like a bar graph. Good. It's not a bar graph, though. This is a histogram. There are slight differences between a bar graph and a histogram. So, looking at this, would you like me to put a bar graph up there? Or do you guys remember what bar graphs look like? Yeah. Between this one and a bar graph, what are some of the differences that you see? Yes.
Histograms.
Yes, big one. Histograms touch. There is no space between the bars. So that's actually very important because if you think about, remember a few classes ago we were talking about the points on a graph. I said you always want to connect them, but you shouldn't because when you connect them, they have meaning. Same concept here. In a bar graph, you don't connect them because between them, there is no meaning, right? They're individual pieces of information. In a histogram, you do connect them because they have meaning. You are ending at the 66.5. That is the upper class of one class and the upper class of the next one. So all data is continuous in that respect. So that's one piece that's very important. What's another part of the histogram that's different than a bar chart or bar graph? Not always. This one does. They don't always have a bell. Has something to do with the bottom. Yeah.
Is it that the numbers are like the number doesn't like group to the bar?
Right. So in a bar graph, each bar had a category underneath that bar. So you would have said 55, 56, 7 through 66, or 67 through 76. That would have been underneath the bar. So if this was a bar graph, you'd wrote 50 or 57 to 66, 67 to 76. You wrote that underneath that. That is a category for that. The histogram it's a continuous line. So you have the 56.5, the 66.5. So there is no necessarily specific category for that bar. That bar is between those two values. Okay. So those are the two main differences between a histogram and a bar graph. Other than that, very similar. They're designed very similar. They're set up very similarly and everything else in it. Now, this is where I said we're going to solve that 0.9 problem by this. So I went from 56.5 to 66.5. Okay. Notice neither of those are in my class, right? I went a half lower and a half higher. That way I know all the values are going to go into one specific spot. So I couldn't put 57 to 66 because then I'd have to have another number for 67. Okay. We want to have it so that there's only those one numbers in between each of the breaks. The nice thing now, though, is if you subtract 66.5 and 56.5, what do you get? 10. What was my class width? 10. Okay.
If you subtract one.
Huh? If you subtracted that from that, you get 10, which is my class width. So that also solves the problem that we have of when we're looking at this, why my class width doesn't come out to be 10 all the time either. Because by going a little bit lower, a little bit higher, we take care of that problem as well. Oh, yeah. Yeah, because the 57 through 66 is going to be in this spot here. So that's why that's 2. Right, it's extending out a little bit past it because all these numbers were whole numbers. Because pulse or heart rate, is heart rate continuous or discrete? It's discrete. Okay, what's the difference between continuous and discrete? How do we determine it? Can you go between it, or is it an instant jump, or can you go between it? So do you go from 90 heartbeats to 91 heartbeats instantly? Yes. Or do you have stuff, or do you go all the numbers between those two? No, you're not going to have 90 and a half heartbeats. 90 heartbeats or 91 heartbeats. Okay. So since they're full numbers, it's discrete, so I don't have to have that worry, that piece in there. Okay. When we looked at the heights in the last problem, there was a decimal point, right? You'd want to go one extra decimal point for this. So this way you don't have, because we could have something that fell in as a 0.5. So I would go an extra half on each one of those. So this way I didn't have that problem. So when you're looking at those things, you want to make sure that your decimals fit so that the numbers will always have a spot to go into and won't ever be on the border between two classes. Okay. All right. So that is a histogram. There's the definition of a histogram for all those that like to write down the definitions. It's exactly what I said. So nothing crazy. Okay. I'm actually going to leave those other 3 up there because I erased them, but because of your question, I'm going to leave. I'm going to put them back. These are all histograms. Every one of these. These histograms, they just don't have any data on them because they're literally just looking at shape. The first one, as you mentioned, is a bell curve. So this is the one that you typically will see. This is the one we're going to be looking at a lot in our class, is the bell curve. If you ever have a teacher, and I highly doubt you will, just because it's going to be a math teacher if anybody does it, say they're curving at a bell curve, run away from the class quickly. Only one person will get an A, and only one person will fail. Even if everybody in the class gets a 90 or above, the lowest grade will fail. That's what a bell curve is. Okay, we'll talk about why that is a little bit later. Not today, later classes. So that's a bell curve. What about the next two? Skewed left, skewed right. Do those look right? Why?
You left is on the right side.
They're backwards, right? Okay. There's a reason for that. They're not wrong. Those are correct. So skewed left and skewed right do not tell you where the hump is. What it's telling you is where the tail is. So it's telling you this. So skewed left and skewed right is telling you how it's being pulled in which direction. Okay. So that tail is pulling the curve to the left, or the tail is pulling the curve to the right. That's what the skewed left and the skewed right is. So it is opposite of the way you would think. Because if you first look at it, you go, okay, I'm looking at where the hump is. No. You're looking at where the tails are. I'm not quite sure why they put that in this section, because we're going to explain why that's the case and understand a lot more when we cover chapter 4 next week. but I know it's in the actual section for homework, so I needed to cover it. All three of those generally have that bell. It's just a matter of where that bell is. Histograms don't have to have a bell curve. Most do when you're looking at normalized data and stuff like that. That's why all the stuff we're going to do later on in the semester with statistics works, because it's all based on that bell curve. However, we don't necessarily have to have a bell curve. The bottom three are also all histograms. One's more uniform. It's pretty much straight across. There's a little peaks and valleys there, but nothing crazy. Then we have the bimodal where you have a couple peaks, and the multimodal where you have multiple peaks. Does anybody know where that term comes from? What's the mode of a set of data?
The average.
Not the average. That's mean. It's the one that appears most often. So bimodal means there's two values that appear most often. Multimodal would be more. Remember, mode's the only one that we can have more than one of those. Okay. It's also the only one that works on qualitative data, not quantitative data. Because any type of data can have a mode. All right. Good. All right. Anybody see a graph like this before? Okay. If I took this graph, hold on. I got to make it a little smaller. Doesn't fit. And made it look like this and totally make all the people who are OCD crazy because that's straight up and down. What does it look like? Looks like a bar. It looks like a bar graph or a histogram, right? So a stem and leaf plot is another way to organize data. Okay. So it is actually a graph, even though it has numbers in it. It is actually the only graph that allows you to actually show your data. So these right here are the same 50 data points we were looking at before. Okay. They are the heart rates. What's the, how many classes do I have in this one? I have 4 classes. What's the class width? It's 10. Stem and leaf plots always have a class width of 10. Okay? Because they are based on our actual number system. That 6 and that 7, that means 67. 6, 9 is 69. 6, 8, 68. 65, 62. And then be 77, 79, and so on and so forth. So that's my stem, that's my leaf. So the only way this works is if it's based on our number system, where the stem is that tens column, the tens group, and then the ones digit is basically my leaves. If we went higher, let's say I added a heart rate of 115. I would have a 10, and then I'd have an 11. And in that one, I'd have a 5. And let's say if I had another 117, I had a 7 there. That'd be 115 and 117. I still have to put the 10 there, even though there's no data there. And I don't put a 0 there, because if I put a 0 there, what's that represent? That represents 100. And I don't have one in 100. Okay. So in this case, I would have 6 classes in there, not 5. Okay. Does that make sense? You rarely ever, so in the definition of a stem leaf plot, you could do negative numbers. You rarely ever see negative numbers in a stem leaf plot. Because most data is positive when you're looking at it. So, but like if we were looking at temperatures and stuff like that, we could definitely have negative values in there. So you could have negative stems. But it would be the same thing. It'd be -0, -0, -1, and so forth backwards in that respect.
For a frequency chart, we're still representing.
Yes. So even when you were doing the frequency table here, like before, so it's actually pulled like this one. Let's say I had, so we did, what was it, 115 to 116 or 115 to 117, right? So we were doing 10 groups of 10. So my next one would have been 107. Actually, I'll have to make another one because it'll be 107 to 10, no, sorry, 116. Yeah. And then 117 to 126. So if I just had that one, that would have been 0, and I'd have had 1 there. Okay. So yeah, so I still would have to have that class there to go above. I can't just skip over that class. But that actually brings up a really important point. Like when we're looking at sometimes, a lot of times you'll see a group of data that has all the data, and then they'll just say 107 and above. They do that a lot of times, in, like when you're looking at incomes, they'll say 0 to 20,000, 20,000 to 50,000, 50,000 to 100,000, 100,000 to 250, and so on and so forth, right? Notice none of the class widths are the same, so it is not a proper frequency table. And then you'll typically see like 250,000 and above, where they group all those in. Because it's not an actual frequency table, the data, if you're putting it into you can put it into a histogram, but it's not really a histogram because the class widths aren't the same. So that normally fits in as a bar graph in that respect, because you're not going to get that nice curve. Because what will end up happening is that last category is going to have a lot more people in it than the ones before it, because it's encompassing a wider range of values. Does that make sense? So for a true frequency table, you need to have all of the classes, and they have to be the exact same class width. So a stem and leaf plot is just another way to graph that. The nice thing is it does show you all the data. We typically do not leave our stem and leaf plots like this. We will typically put them in order. So this way you also then can figure out middles and averages and all this other stuff. And some of the stuff that we're going to talk about in, I'm not sure, Monday or Wednesday next week, in chapter 4, when we're looking at box and whisker plots and those type of things, a stem and leaf plot actually helps us do that a lot better, easy, because it helps us put that information in order, which is nice. You also can have what's known as back-to-back stem and leaf plots. So if you only have one, you typically always go to the right. However, you can have one, 2 of them that you're looking to compare the data for, and you can go both directions. The stem is in the middle, the leaves are on either side of it. So in this respect here, if we're looking at this middle row right here, Ruth had a season of 11, Bonds had a season of 16, and a season of 19. And this one, Ruth had 54, 59, and 54, and Bonds had nothing. The 0 one is no different. The 0 one, the nice thing is you can basically just ignore the 0. Bonds had 5. However, notice how there's a 0 here. Ruth had a season that he had no home runs. And since this is showing all their seasons, they had to put that information in there. But you can see like these 2 over here, there's nothing here. Means Bonds never had a season with 50 home runs. He never had a season with 60 home runs. He had one with 70 home runs. So, okay, so we can have a back-to-back stem and leaf plot where we're showing that information on both sides. It allows us to start looking at comparing types of data, seeing how, like in this case, we can look at that Babe Ruth had was a lot more consistently higher. He had a lot more of those 40 and 50 game seasons, stuff like that, than Bonds did. Bonds had some 40s. Most of them were in the 30s and the 40s, and then he had that one outlier season, that 73. Does that make sense? Yes.
Essentially, looking at like if you're looking at, class one, it would just be 16 for bonds and 11 for Bruce.
So if we're looking at the class one, it would be 11 for Ruth and 16 and 19 for Bob. He had two. Yeah, he had those two in there.
Is we select Instagram or staff?
You actually could make a histogram that goes both directions. I wouldn't do this as a stacked histogram. So in this case, it actually would be two histograms. And you can have a histogram that goes both ways that looks just like a stem leaf plot. So if I made, let me actually get rid of the numbers. So I could do, and you would literally have it going both directions. So that's how this bar graph would actually look. Huh?
People make stuff.
Yep. Because remember, the whole goal of any type of graph is to look at the data and figure out what's going on, right? So when we're looking at situations like this, we've got the data there. Sometimes making colors and having it different directions, stuff like that, will help you visualize what's going on. So we saw it last class. There's a lot of crazy looking graphs. Like not every graph is like the standard type of graph that you would normally think of. So there's a lot of different types of graphs out there. So yeah, people make anything to visualize information. And the more we have computers that can actually do it in different ways, we're seeing a lot more visualizations of those types of graphs. So, well, a histogram is just, it's a way to organize the data into bars so we can actually see those classes. And it's just the most common one. It's like a bar graph. Everybody knows what a bar graph is. Everybody can read a bar graph. So a histogram it allows anybody to actually understand what's going on. So that's why we use that a lot more. But we're starting to see, and I'll actually, hold on. Let me finish the last couple and then I'll show you some of the other graphs that they're talking about too in the book. So what type of graph is this? Almost. You got one more word you got to get. It's not a scatter plot. A scatter plot, you have to have X and Y. Huh? There's no lines. There's dots, though. It's a dot plot. So, what's the class width of this? 1. Each of those dots represent one piece of information. Okay? So, when you have it stacked, that's counting how many wins they had. So, in this case, Chicago had 3 seasons that they won 66 games. Okay? So, in this case, every one of those dots is an individual data point. They're not actually combining them in any respect. All right? So, my class width is 1 in this case. So, we went from a stem leaf plot where your class width is always 10 to a dot plot where your class width is always 1. Okay? So, again, this is not going to work for every type of data. Sometimes, like if we looked at this in terms of the heart rates, it might work, but it wouldn't show us as much or as much of a curve as we would want to actually see what really was going on in this case. This one, the way the data points work out, it's fine. We have 100 and something data points, so we could easily see that. Yes, in one season they only won 65 games. In one season they won 103. In one season they won 38, which the Chicago White Sox might do this season. Sorry if anybody's a Chicago White Sox fan. All right. Now we can also have, so this is where some more of the more modern style graphs. So you can have graphs that look like this. This one's more of a line style graph, but still a graph. So this graph right here, okay, what type of data is this? There's two types of data we talked about way back. It was time series and cross-sectional. Is this a time series or cross-sectional? This is a time series. How do we know it's a time series? Because it goes in time and we're looking at data points over time. So this is a time series. So this is two graphs comparing two different things. Looking at, when we're doing things like this, we'd want to pick two things that have some kind of relationship to each other, or a relationship that we would assume to be there. It might not. In this case, we're looking at sea level change and global temperature change. And there should be a relationship between those two things. I find these graphs, like, I love these graphs. This one, these are known as geospatial graphs. This is a great way to like visualize data. So in this case, this is the county obesity population. So there's a number of people in each county that would be considered obese. So the darker the color, the more obese people live there. Okay. And you can see color shadings on where, now we have this big section in the middle that's pretty much all white. Because nobody lives there. Or very few people live there. So the other thing you'll notice is counties get bigger out west. West has a lot larger counties than we do back in the Northeast. So where there's like all these little dots over here, there's a lot bigger ones out here. Same thing in Alaska. There's nobody that lives up through here. That's actually all federal, a national forest. So these are geospatial graphs, they're called. Huh? Yes. A population graph would definitely help in this respect. But we also could, instead of doing the number of people, we could do the percentage of the population. Would probably be a better way to look at this type of data. So I'm trying to find, there was another type of graph that's really kind of cool. And I can't find one that I like. Actually, I have no idea what this data shows, but I'm going to see it in a second. These are another graph that people see quite often that you'll see. So they use the colors to represent different types of stuff that they're doing. This looks like it's a, so this is studying, chores, wasted time, social time. So it's like, and I'm going to guess this would be work. So they're going through and they're breaking up their day. So they use, or their time over the month and what they're actually spending their time on. So you can see how, like, you have the whole 100%. So it's like that pie chart, but then it's broken out, going further and further out from that respect. So we have lots of different ways that we can do graphing. And I think with AI, you're going to see the computers making up even other ways to visualize the data and that information. So, all right. So how do I find class width? Very good. Maximum minus the minimum divided by the number of classes. And then go up a reasonable amount from there and find the number that you want to use. All right. Any questions? Next class on Monday, make sure you have a calculator. It can be on your phone, totally acceptable, but make sure you have a calculator that you know how to use, because we're going to be doing some calculations. So, yes.
Do you think that's like?
Well, oh, tracking you're breaking your stuff down that much? Well,